Okay, so let us discuss Poisson's ratio. But before that, let us recall the concept of strain and let's have this situation. The uniaxial loading. So for example, we have a circular rod. I carry a tensile force P along x-axis. So uniaxial, we are just applying a force in one direction. So this tensile force basically will cause a deformation along the x-axis. So if you are to compute for the strain along x-axis, and the strain along x is the ratio of the deformation along x divided by the length of the sample. That will be the strain along x. So what about the strain along y and the strain along z? So for example, we have this as the initial diameter of the sample. So let's say the initial diameter of the sample is, we have D. So basically, this elongation, this is a positive strain. This positive strain will cause a decrease in the diameter of the rod. So let's say this will be the final diameter of the rod. Let's say this is a D prime. Take note that the change in the diameter will be equally distributed in all directions for a uniaxial loading. And since we have a circular section. So let's say if we are to distribute the change in diameter in one axis, let's say this is along y, this is the delta D over 2, the other half will be on this portion, that is the delta D over 2. So we have equal strain for this one. The equal strain along y and the strain along z. How do we compute for the strain along y and the strain along z? Since we have a decrease in diameter for a tensile force along the x-axis, that is basically equal to the negative ratio, that is the negative delta D divided by our initial diameter. So the same concept for strain, that is the change in length along x divided by the length. The strain along y will be the change in diameter divided by the diameter. So what is the equivalent of the Poisson's ratio? So you have the Poisson's ratio is equal to the negative strain in the transverse direction. So for this case, elongation along x decrease in dimension in the transverse direction. This is negative strain in the transverse direction, and our main axis for this case is x-axis. So we have the strain along x. So if you are to compute for the equivalent of the strain in the transverse direction, this is the same as the strain along y and the strain along z. So we have it, for example, we have the Poisson's ratio. This is, I'll be using the strain along y divided by the strain along x. We have the strain along y is equal to the negative Poisson's ratio, the strain along x. So basically, what is the equivalent of delta? That is the force along x, the length, divided by the area, times the modulus of elasticity, divided by the length. We may cancel the length. So we have the strain along x is the force along x divided by the area divided by the modulus of elasticity. So what is force over area? So force over area is basically stress along x divided by the modulus of elasticity. So again, for this case, we have the equivalent of the strain along y is also equal to the strain along z is equal to the negative Poisson's ratio multiplied by the strain along x is the stress along x divided by the modulus of elasticity. So this is for a uniaxial loading, for the Poisson's ratio. So for example, how do we compute for the final diameter? By the way, so the final diameter is basically equal to your initial diameter plus the delta D. Take note that if we have a decrease, we have a negative sign for the decrease or the change in diameter. Then if we have, for example, increase in diameter, that will be positive. Okay, this is just a general equation. So let's have one example. So let's have this example. For example, we have this rod having a length of 1 meter that is carrying a tensile force of 200 kilonewtons. Let's say the properties, we have the diameter is equal to 30 mm, the modulus of elasticity of the material is 150 gigapascals, and let's say the Poisson's ratio of the material is equal to 0.32. So we are required to compute for the final diameter after the application of the tensile force. So let's have the strain along Y is also equal to the strain along Z for this case. That is the delta D divided by the initial diameter. But if we are to compute for the strain of Y or the strain along Z, that is basically equal to the negative Poisson's ratio, the stress along X divided by the modulus of elasticity. So by the way, if we are to deal with stresses using this formula, we are to use positive sign for a tensile stress if the stress is for tension, and negative sigma if the stress is under compression. Alright, so positive sigma for tension, negative sigma for compression. So we have now the equivalent of the strain along Y or the strain along Z is equal to negative, our Poisson's ratio is equal to negative 0.32. So what is the equivalent of stress along X? The stress along X is the force divided by the area. So that is the force, what is our force? We have abusing 200,000 newtons. This is divided by the area, the diameter is 30 mm. So this is 30 squared pi divided by 4. So this is the equivalent of the stress, this is in terms of square millimeters, divided by the modulus of elasticity. We have 150 gigapascals, or the same as 150,000 megapascals, or that is the newtons per square mm, since strain is unitless. So we have the value of the strain along Y equal to the strain along Z. So this is equal to negative 0.32. This is multiplied by 200,000 newtons divided by the area, that is 30 squared pi over 4. It will be divided by the modulus of elasticity, 150,000 megapascals. So we have a negative strain. This is negative 6.036 times 10 raised to negative 4. So again, the negative sign indicates that we have a decrease in diameter. Okay? The diameter will decrease since we have a tensile force. Let's say that is along the x-axis. So how do we compute for the change in diameter? We have the strain along Y is equal to the strain along Z is the ratio of the change in diameter divided by the initial diameter. So it's the value of that strain. We have negative 6.036, this is times 10 raised to negative 4, is equal to the change in diameter divided by the diameter. The diameter is equal to 30 mm. So we are having the change in diameter equal to, it is equal to negative 6.036 times 10 raised to negative 4 multiplied by 30. And it will be, I'll be using 3 decimal places for this one. This is negative 0.018 millimeters, or millimeter. That's a very small value. Negative 0.018 mm. So how do we compute for the final diameter? The final diameter D prime is equal to the initial diameter plus the change in the diameter. We have the final diameter is not equal to, we have 30 millimeters plus this one, it's a negative. We have negative 0.018. So you have the final diameter after the application of 200 kilonewtons. That is 30 plus negative 0.018. Our answer will be equal to 29.982 millimeters. So this will be the final diameter. Alright, so this will be our solution for this case, uniaxial loading. So the next situation will be the biaxial loading. Okay, so for example, we have a material carrying axial forces into directions. So we have, for example, this is the axial force along x. Let's say this is px, and we have a force along y. Let's say this is the piece of y. So if you are to recall what is the equivalent of strain, strain is the deformation divided by the length. And we have strain is equal to deformation is the force multiplied by the length all over area times the modulus of elasticity. This is divided by the length, cancelling the length, and again, force over area is stress. So we have the equivalent of strain is basically the stress divided by the modulus of elasticity. So for example, we are to determine the strain along x-axis. That is, the strain along x-axis is basically the summation of all the strains. So we are just to consider what will be the effect of the strain along y and the strain along x-axis. So this is the same as the strain along x is equal to, how do we compute for the strain? That is, we have the stress along x divided by the modulus of elasticity. We are just to add the effect of the strain along y. So that is plus, but for this case, we are using the negative sign for the Poisson's ratio. I multiplied by the stress along y divided by the modulus of elasticity. So we can generalize, this is the strain along x, we have to factor out 1 over e, this is multiplied by the stress along x minus the Poisson's ratio multiplied by the stress along y. Or for example, instead of the strain along x, we are computing for the strain along y. So all we have to do is follow this pattern. That is 1 over the modulus of elasticity. This is multiplied by the stress along y minus the Poisson's ratio multiplied by the stress along x. So this is how we compute for the strain, considering we have biaxial loading. So on the case of triaxial, so for triaxial loading, all we have to do is consider our three axes. We are considering a material carrying three forces in our three axes. So for example, we have a force along x, and let's say a force along y, and a force along z. So the material is carrying or subjected to three forces on the three axes. So how do we compute for the strain? The strain per direction. It is similar to this one. So you have the strain along x. Basically, all you have to do is perform the summation of the strains in all directions. So you have the strain along x is equal to the strain along x, that is sigma x over the modulus of elasticity. We are just to consider the effect of the strain in the y direction and on the z direction. So we have that is plus, we have negative Poisson's ratio, the stress along y divided by e, plus we have negative Poisson's ratio divided by the stress along z. This is divided by the modulus of elasticity. Or we are to simplify, we have the stress along x not equal to 1 over the modulus of elasticity multiplied by the quantity stress along x. We factor out this Poisson's ratio multiplied by the stress along y plus the stress along z. So this is how we compute for the strain along x. So computing for the strain along y, all you have to do is follow this pattern. This is 1 over the modulus of elasticity multiplied by, so this is now stress along y minus the Poisson's ratio multiplied by the stress along x plus the stress along z. And lastly, we have the strain along z is now equal to 1 over the modulus of elasticity multiplied by the stress along z minus the Poisson's ratio multiplied by the stress on x plus the stress on y. So this is how we compute for the strain, considering triaxial loading. So let's have an example. So let's have this example. So for example, we have this sample with a dimension of 30 mm by 40 mm by 20 mm. It carries 3 forces in 3 directions. So we have the axial force along x is 60 kilonewtons under tension. We have the force along y that is 45 kilonewtons also under tension, and we have the force along z that is 48 kilonewtons compression. Let's say the modulus of elasticity of the material is equal to 200 gigapascals, and the Poisson's ratio is equal to 0.30. So we are required to compute for the strain along x, the strain along y, and the strain along z. So first, we need to determine the value of the stresses in each direction. So basically, we have the stress is equal to the force divided by the area. So we have the stress along x is the force along x divided by the area. We have the stress along x this is equal to 60 kilonewtons or 60,000 newtons. What is the area perpendicular to this one? That is 30 by 40. So this is divided by 30 by 40. This will be in terms of square millimeters. So we have the stress along x is equal to, what is that value? We have 60,000 divided by 30 by 40. So that is equal to 50. Take note, this is under tension, so 50 newtons per square mm is the 50 megapascals. That's the stress along x. We have sigma y is equal to py divided by the area. So we have the stress along y is equal to, we have 45 kilonewtons or 45,000 newtons divided by, what is the perpendicular area? So this one, that is 20 mm by 30 mm. So you have 45 divided by 20 by 30. This is square millimeters. So you have the stress along y. Take note, this is the same as a tensile force. So we have a positive sign for that. We have 45,000 divided by 20 by 30. So we have 75. Is equal to 75 megapascals. So this is the stress along y. And lastly, we have the stress along z is equal to the force along z axis divided by the area. We have stress along z is equal to, we have negative 48,000 newtons. So I'm using the negative sign since it is under compression. So negative 48,000 newtons, and the perpendicular area is, we have 20 mm by 40 mm. So this is divided by 20 by 40 square millimeters. So we have sigma z is now equal to, we have 48,000, that is divided by 20 by 40. So we have, this is negative 60 megapascals. So again, it is negative. For this one, it is under compression. So if we are now to compute for the strain, we have the strain along x is equal to 1 over the modulus of elasticity multiplied by the stress along x minus the Poisson's ratio multiplied by sigma y plus sigma z. So all we have to do is substitute. So this is the strain along x is equal to 1 over 200,000 megapascals. To be consistent with our units, I'll be using 200 megapascals, the same as 200 gigapascal. So the stress in x is equal to 50 minus the Poisson's ratio is 0.30 multiplied by sigma y is 75 plus And we have sigma C is equal to negative 60 megapascals. So basically, strain is unitless. So it's equal to 50 minus 0.3 of 75 minus negative 6. 75 plus negative 6. So that's equal to, we have positive 2.275 times 10 raised to negative 4. We have a positive strain along the x-axis. Then we have the strain along y is equal to 1 over E. I'll just be placing the solution here. We have the strain along y is equal to 1 over E multiplied by sigma y minus the Poisson's ratio multiplied by stress along x plus the stress along z. So we have the strain along y is equal to 1 over 200,000 megapascals. What is the stress along the y-axis? That is equal to 75 megapascals minus 0.3. Stress along x is equal to 50. Then stress along z is equal to negative 60. Okay, so we have the strain in the y-axis. Okay, so we have 75 minus 0.3 of 50 minus 60. This is divided by 200,000. So we have that as 3.9, also positive. 3.9 times 10 raised to negative 4. So we have a positive strain along y, which means we'll be having an increase in dimension in the y direction. And lastly, we have the strain along z equal to 1 over E is multiplied by the stress along z minus the Poisson's ratio multiplied by the stress on x multiplied by stress on x plus the stress on y. So we have, this is E sub z is equal to 1 over 200,000. Our stress on z is equal to negative 60 megapascals minus 0.3 multiplied by stress on x is 50. Stress on y is 75. So we have the strain on the z-axis is now equal to negative 60 minus 0.3 of 50 plus 75 divided by 200,000. So we have this value is negative 4.875. This is times 10 raised to negative 4. We'll be having a shortening on the z direction or z dimension of this given sample. So this will be our solution.